Hello and welcome to Principles of Mathematics, lesson number 10. In this lesson, we're going to learn about division of whole numbers. We'll be looking at the meaning of division through various models, the inverse relationship between multiplication and division, the special cases of division by 0 and 1, division algorithms including the standard algorithm, division in number bases other than 10, and mental division skills and estimation techniques. The main models that we use to teach division include the set or partition model. In this model, the set of elements representing the dividend is partitioned into a divisor number of subsets. So if you're not familiar with those terms, remember that when you take a number like say 15 and divide it by 3, we end up with 5, of course, and the remainder is 0. So the number that's being divided is called the dividend. So the 15 here is called the dividend. The number that's being divided into 15, that's called the divisor. The result is the quotient. And in this particular example, the remainder is 0. So that's what we're talking about in this particular case with these words such as dividend and divisor number of subsets. We'll look at an example of that in a minute and it'll make more sense. The missing factor model basically says A divided by B is a unique number C as long as B times C equals A. Once again, we'll look at an example and that'll make total sense to you. And then the repeated subtraction model. This is in opposition to the multiplication, which we know is repeated addition, and that most people are comfortable with, but sometimes people get surprised when you tell them that division is nothing but repeated subtraction, and we'll see how that actually works out very soon. All right, so here's a look at the set model. Suppose we have 18 cookies and we want to give an equal number of cookies to each of 3 friends, Bob, Dean, and Charlie. How many should each person receive? Of course, we make a set with all 18 of the cookies in there, and we want to break it up into 3 equal parts, and we just need to see how we could possibly partition this into 3 parts, and we can see that that can be done easily in this manner, and that means each of them is going to get 6 cookies. A very basic approach which students can absorb very easily. The missing factor number is also a very useful and easy to comprehend model. So for example, here we're saying we want to divide 18 by 3. Now, whatever number that ends up being, we know that that number times 3 should give us 18. So we'll just call that number something like C. We say 18 by 3 is equal to C if and only if 3 times C is equal to 18. So we ask ourselves 3 times what number gives us 18, and of course we know that that number would have to be 6. Somewhat more abstract than the set model, but still easy to grasp. Finally, we have the repeated subtraction model. So suppose we have 18 cookies, and this time we want to package them in cookie boxes that hold 6. How many boxes are needed? So this is when we just start subtracting. So we say, what if we take 1 6 away from 18? That leaves 12. Can I take any more 6s away? Yeah, I can take 1 more away, and that leaves me 6. And finally, if I take one more 6 away, that's going to leave me with 0, right? So if I do 6 minus 6 again, that gives me 0. So since we did that 3 times, we know that there are going to be 3 6s that fit inside 18. Therefore, 18 divided by 6 equals 3. So that's the repeated subtraction model. In a way, it would probably be the least efficient way of doing division. But as far as understanding what's going on, in that we're trying to see how many of the divisors fit inside the dividend, it makes a lot of sense. We formally define division of whole numbers using the missing factor model. We say for any whole numbers a and b with b not equal to 0, in other words, we can't divide by 0, a divided by c if and only if c is the unique whole number such that b times c equals a. The number a is the dividend, as we mentioned before, and b is the divisor, and c is the quotient. All right, so in other words, c would go here, and we're dealing right now with situations that do not leave a remainder, so that remainder would be 0 at this point. We'll deal with non-zero remainder situations very soon. All right, let's now say that we do divide a number a by another number b, and let's assume that, of course, b has to be non-zero, that b goes into a q times, but this time not necessarily perfectly, so that in the end we have some remainder r. So the way that we write this, let's for example look at an example. Let's say we're dividing 17 by 3. We know that 5 times 3 will give us 15 with a remainder of 2. And this is where the division algorithm stops, because 3 no longer goes into 2, so we don't go any further. So we say 2 is the remainder. Notice that we can write this in the following way. We can say 17 equals 3 times 5 plus 2. So 17 has 3 5s in it, but then once we take those 5s out, we're still left with 2. So that's what we mean by the remainder. So if we do this analysis for this general situation, it would look like this, right? We would say a instead of 17 equals bq, right? 3 times 5 instead of 3 times 5, we write the general bq. And then plus, instead of the special case of 2 here, we just write the general case of r. And this is called the division formula, and the process is known as the division algorithm. And we're going to be encountering this again, so make sure that you understand what just happened here, how we went from this specific case and we generalized it for division as an operation, and we will see it again soon. Okay, here we have a problem that tests our knowledge of the division algorithm and the division formula. We want to know if 123 is divided by a number and the remainder is 13, what are the possible divisors? All right, if we just write that out like this, so we're dividing 123 by some number, which we can just call b. Normally we use lowercase d for that, but this textbook has an affinity for b, so I'll just stay with that. And the remainder is 13. We also don't know what the quotient is. So remember that the division algorithm, let me remind you, if you divide A by B, the quotient is Q and the remainder is R. The division formula tells us that A equals BQ plus R. Now let's go ahead and write the division formula for this particular case we're dealing with. So instead of A, we have 123. BQ is going to turn into itself because we don't have either B or Q. So BQ remains BQ. Plus, we do know the remainder, that's 13. Okay? So we go ahead and notice the fact that B does have a restriction on its value, right? It obviously can't be less than or equal to 13 because otherwise we would have continued the operation, right? So B has to be greater than 13. So let's write down that restriction because we're going to need it later. All right, so let's see what the product of BQ is going to look like because we can't really tell what B or Q is right now, but we can tell what the product is going to be, right? By just solving for it. So we're going to go ahead and subtract 13 from both sides. And we will end up with BQ being equal to 110. Okay, so now we know what the product of B and Q has to be, right? And we also know, so these are the two things we know. We know that B is greater than 13, and we know that the product of B and Q is 110. So if we take a look at the different products that give us 110, we'll probably get very close to our answer. So let's look at some ways. Like we know we can do 1 times 110. We know we can do 2 times 55, 5 times 22, or 10 times 11. Now, later on in the class, I'm going to show you how to come up with these pretty effortlessly using a process called prime factorization. But for the time being, you can just play around with the numbers and you'll see that these are correct. Now, of all these factors that give us the product of B and Q, there are only a few that satisfy this requirement, right? And if we go ahead and circle them, you realize that the 22, the 55, and the 110 are the only possible values for B because those are the only numbers that are greater than 13. So therefore, the three circled numbers in red would be the ones that we're looking for. Those are the only possible divisors because those are the only ones that are greater than 13. So this restriction of B being greater than 13 played a big role in us finding the proper answers for this question. All right, that's a nice problem in getting us to understand the division algorithm. Make sure that you understand it before we proceed. All right, when it comes to division by 0 and 1, 0 is one that you have to really pay close attention to because 0 cannot be a divisor because let's see why that could be. Let's say that we have 6 divided by 0 and we want to know what number that could possibly be. Notice that that would mean, if we look at a simpler example of 6 divided by 2 is 3, what does that mean? That means 2 times 3 is equal to 6, right? So this would have to mean that 0 times that number has to equal 6. But remember, 0 times any number is 0. So by assuming that 6 divided by 0 is well defined, we reach a contradiction. So this tells us this is a contradiction, because we know 0 is not equal to 6, therefore 6 divided by 0 is undefined. This is a quick example of a proof by contradiction. If you wanted to really formalize it, you would start by saying, suppose 6 divided by 0 is well defined. And not only, since it's well defined, we just give it a name, and that 6 divided by 0 is n. Then that would imply this, which it would imply that 0 equals 6. Therefore, we've reached a contradiction. So therefore, our initial assumption that 6 divided by 0 is well defined was incorrect. So therefore, 6 divided by 0 is undefined. All right. Now, while dividing by 0 is problematic, even if the dividend is 0 itself. Okay, so you cannot divide by 0 no matter what the dividend is, whether the dividend is 0 or any number other than 0. Dividing 0 is no problem, as long as you're not dividing by 0 again, because remember, 0 divided by 0 is undefined as well. So 0 divided by 5. So I have absolutely no money in my pocket. I have $0, and I want to split that evenly between 5 friends. Can I? Sure. I'm going to give them $0 each, right? So you can divide 0 by as many people as you want, or you can divide 0 by any number that you want, and you're still going to get what? 0. So 0 divided by any number is well defined, and it's 0, but never ever divide by 0. Whether you're dividing a non-zero number by 0 or 0 itself, in both cases you're going to get an undefined answer. So be very careful with 0 when it comes to division. All right, here we have a really nice visual showing us the relationship between addition and subtraction. Those are inverse operations, as are multiplication and division. And another nice relationship is that we know that if we do repeated subtraction, we end up with division, and if we do repeated addition, we end up with multiplication. So a nice visual showing us the relationship between all 4 basic operations. All right, so we did mention this particular rule for exponents in our last lesson. If you recall, this is called the quotient rule. Let's look at a quick example of how you could use this rule. Normally, we write it in the form of a quotient like this. A to the m over a to the n equals a to the m minus n. I showed you an example of so that you could understand why this becomes true. Like if you have x to the 5 over x squared, notice that 5 factors of x being multiplied on the top and 2 factors multiplied on the bottom, then 2 of those factors on the top will cancel these 2 on the bottom, leaving just ones, right? And so we end up with x cubed. So the quick way of getting that, of course, using the quotient rule, as long as you have the same base on both your powers, you can apply the quotient rule, and you could have just gone x to the 5 minus 2. This, of course, is priceless because it helps you understand why the quotient rule makes sense. Now, how about a quick example of how we would use that? Let's say I want you to simplify 8 to the power of 5 divided by 2 cubed, okay? Without using a calculator, obviously. So what we're going to do is we're going to see if there's any way we can get these 2 numbers both have the same base. these two powers, right? And we notice that 8 is indeed a power of 2 itself. If you recall, 2 cubed is 2 times 2 times 2, which is 8, right? So what we can do is we can replace that 8 with 2 cubed, and then we have it raised to the power of 5 over 2 cubed. Now, on the top, we have a power rule application, because if you remember, if you have a to the m and then you want the nth power of that, you keep the base a and you multiply the exponents, right? So on the top, we really have 2 to the power of 15, and on the bottom, we have 2 cubed. Now we're going to go ahead and apply the quotient rule. Let me erase this real quickly. And we're going to end up with 2 to the power of 15 minus 3, which is 2 to the power of 12. Now, normally we can just leave these in this form. If they wanted you to multiply it out, then make sure you don't make the mistake of thinking that this is 24. That's a very common error. You never multiply a base and an exponent. This is actually a very large number. Why? Because you have to write 12 factors of 2 and multiply them. Okay, so just to give you a feel for it, let's take a look at what it actually is. So remember, what the calculator is about to give us is the result for this. 2 times 2 times 2, times 2. How many factors? 12. So here we just go, clear all that. So we just go 2 to the power of 12, 4096. So nowhere close to the erroneous answer of 24, okay? Never multiply a base and an exponent. That's just, it's an operation that you never perform. There's no day in life where you're going to walk into a math class and today we're going to multiply bases and exponents. No, it just never happens, just because of the very definition of exponents, right? So stay away from that with all your might. All right, let's move on. All right, when it comes to teaching young students about division, base 10 blocks, always come in extremely handy. So we're going to take a look at this long division using base 10 blocks. And since I don't have the great set of manipulatives for this, we'll go ahead and get help from YouTube once again. All right, so here's a nice video showing us how to divide using base 10 blocks.
Welcome to an example of partitive division, also known as sharing or grouping division, using base 10 blocks. We are given the quotient 525 divided by 3. One way to view this quotient is to begin with 525, and because we are dividing by 3, we try to form 3 groups, with each group containing the same amount. We can also view this as having $525, and again, because we are dividing by 3, we want to share $525 equally among 3 friends. Using base 10 blocks, we begin by modeling 525. For review, using base 10 blocks, a flat equals 100, a rod or long equals 10, and a unit or bit equals 1. To model 525, we have 5 flats, which equals 500, 2 rods, which equals 20, and 5 units, which equals 5. And now, because we're dividing by 3, we will begin sharing the 5 flats among 3 groups. We will place 1 flat into each of the 3 groups. We'll call this group 1, group 2, and group 3. Notice we're left with 2 flats, which we could not share equally among the 3 groups, and therefore we need to perform an exchange. 1 flat is equal to 10 rods, and therefore we exchange 10 rods for this flat and 10 rods for this flat. We will now exchange these 10 rods for this flat, And now we'll exchange 10 rods for this flat. So now we'll perform the exchange. Again, we're exchanging these 10 rods for this flat. Notice now we have 10, 20, 21, 22 rods, which we need to try to share equally among the three groups. And because 7 times 3 is equal to 21, we know we can share 7 rods with each of the three groups. Let's go ahead and do this. Notice how we still have 1 rod remaining. We cannot share this rod equally among the three groups. We need to perform another exchange. 1 rod equals 10 units. We will now exchange 10 units for this 1 rod. We will now exchange these 10 units for this rod. Notice how we have a total of 10 plus 5 or 15 units, which we want to share equally among the three groups. And because 15 divided by 3 is equal to 5, we can share 5 units with each of the three groups. Notice how there are no base 10 blocks remaining, and each group contains 1 flat, 7 rods, and 5 units, which is equal to 100 plus 70 plus 5, or 175. This shows 525 divided by 3 equals 175.
All right, very nice example. Notice that he uses the term rod where we normally use the term long. They're the same thing. Those names are interchangeable. So that's a very, very beautifully done example showing how to use base 10 blocks to explain division to younger students. Now we will look at how we can use repeated subtraction on our way to developing the standard division algorithm. So dividing 726 by 6, we basically ask ourselves, we try to subtract as many sixes as we can as quickly as we can. So we notice that we can definitely take 100 sixes away, right? And that'll be 600. So that still leaves us 126. Now we ask ourselves, how many more sixes can we take away? Well, we know we can definitely take 10 more away. That leaves us 66. We take 10 more away. That leaves us 6. And then finally, we take 1 more off, and that leaves nothing. So this is how we add these. We had 100, then 10 more, and then 10 more, and then 1. So 121 sixes were taken away. Now, instead of doing these tens, we could have just, at the point after we took the 600 off, we could have, and left with 126, we could have taken 26s off, since we knew that 20 times 6 is 120, to make this a little bit quicker as an operation. And then we end up with 1 more, and then that's how we get our 121. So both of these are kind of working toward the standard division algorithm. So sometimes we represent the division algorithm like this. We say 6 goes into 726 100 times, and multiply, you get 600, subtract, you get 126. How many times does 6 go into that? 20 times. We write that here, and we're left with 6. And how many times does 6 go into 6? 1 time. Combine those, you get 121. Now, normally, we don't show all that, right? We show the shorter version. This is our standard algorithm for division. So basically, we only focus on 1 at a time like this. So we say 6 goes into 7 once. 1 times 6 is 6. We subtract, we get 1. Bring down the 2. 6 goes into 12 twice. 2 times 6 is 12. That leaves 0, so we bring the 6 down. And then we know that there's 6 goes into 6 once. So 1 times 6 is 6, and we end up with a 0 at the end. So these are different ways of approaching the problem, but we usually just end up with this highly efficient standard algorithm. Okay, everything we've looked at so far has been in base 10, so how about bringing back your favorites, right? Other bases. Yeah, they can get a little tricky, but again, with practice, you get better and better at them. So here's the multiplication table for base 5. We already saw this in the previous lesson, and we know why some of these numbers come about. So let's just review. Like when we do 2 times 4, why do we have to write 1, 3? Well, think about it. 2 times 4 is 8, right? Now, in base 5, there is no 8 because we can only use digits 0 through 4. So we just have to find out how many 5s, how many 1s, etc. are in 8, right? Because the powers we can deal with are 5 to the 0, 5 to the 1, 5 squared, 5 cubed, etc. So 5 to the 0 we know is 1, 5 to the 1 is 5, 5 squared is 25, 5 cubed is 125, etc. We of course don't have any 25s in there, but we do have 1 5, and when we take that out, that leaves 3 1s. So we know that 8 can be written as 1 3, and that's where that 1 3 comes from. Let's remember where the 2 2 comes from. It's easy to get tempted and say 22, but this is in base 5, so we read it as 2 2. 3 times 4 is 12 in base 10, so we know we can't write 12. So we ask ourselves, how many 5s and how many 1s are in 12? We know there are 2 5s, that will give us 10, and therefore we're left with 2 more 1s that we need. So that's where the 2 2 comes from, etc. So it's good to keep that in mind as we try to divide in different bases, at least in base 5. For base 6, 7, 8, these would of course change to 6 to the 0, 6 to the 1, 6 squared, 6 cubed, etc. All right, here we look at 2 different approaches for dividing 3, 2, 4, 1 in base 5 by 4, 3 in base 5. This method is actually longer but quite intuitive and simple to use, because we know that in base 5, just as in base 10, when you multiply by 1 0, that's just going to add a 0. We've already seen this in previous lessons. So if I just go ahead and multiply 10 by 1 0 by 4 3, I end up with 4 3 0. Now we subtract that, and remember we're subtracting in base 5, right? So be very careful and go back to review how we do a subtraction in base 5. Now, 0 from 1 is 1, 3 from 4 is 1, 4 from 2, we can't do it directly, we have to borrow. And remember, the way we do that, we scratch out the 3, we make it a 2, and now don't forget, we don't add just a 1, we're adding a 5 here, right? So 5 and 2 will give us 7. 4 from 7 gives us 3, and the 2 can just come down. So we get 2, 3, 1, 1. Now we repeat the process. We multiply by 1, 0 again. We get 4, 3, 0. We do the subtraction again. And if you do it just like we did up here, you end up with 1, 3, 3, 1. We do it one more time. We end up with 4, 3, 0 again, and we subtract. Now, we can't get 4 in there anymore because this is not large enough, because we know we would get 430, and 401 is not large enough to handle that. So this time we go ahead and start trying smaller numbers. Now, remember that if we multiply, for example, 4, 3 base 5, let me show you on the side here. If we take 4, 3 base 5 and multiply it by 2 in base 5, we end up with what? Let's see. 2 times 3, that's 6. Of course, we can't write 6 in base 5, but we know that's 1, 5, and 1, 1. So we put the unit here and put 1 up here. And now we have 2 times 4, which is 8, and 1, which is 9. Of course, we don't write 9. We write in base 5, we write 1, 5, and 4 ones. Remember? So we get 1, 4, 1 base 5. That's where this comes from. Now we subtract, and we end up with 2, 1, 0. We can try 2 again. Multiply 2 by 4, 3. We end up with 1, 4, 1 again. And when we subtract, we get 1, 4. This is where we stop, because now in base 5, 4, 3 base 5 is certainly larger than 1, 4 base 5. So that's when we know we need to stop. Now just combine these factors here. 1, 0, 1, 0, 1, 0. That'll give you 3, 0 in base 5, just as it would in base 10, right? Because 0 plus 0 plus 0 is 0, and 1 plus 1 plus 1 is 3, and none of those have digits higher than 4, so we're good to go. So, and then we have 2 more and 2 more, so we get 34, and the remainder is 14 right there. Now, this is a kind of, like I said, long process, but it's really simple. So you could do it directly, just approach it the way we normally do. We go 4, 3, doesn't go into 3, 2, but it may go into 3, 2, 4, right? This is when you want to know at least the first few products of 4, 3 by numbers like 2. We know 4, 3 times 1 is just 4, 3. So let's look at 4, 3 base 5 times 2, which we did over here. That was 1, 4, 1, okay? So we can do better than that, right? Let's try 4, 3 base 5 times 3 base 5. So notice 3 times 3 is 9, which is 1, 5, and 4 ones, right? So we put the 4 here and a 1 here. 3 times 4 is 12, and 1 is 13. So 13 in base 5, remember that's 2 5s and 3 1s, right? Base 5. All right, so that's where this 2, 3, 4 comes from. Then we do our subtraction, and we end up with 4 from 4 is 0, and we can't do 3 from 2. We have to borrow like we did over here. So when this character becomes 2, we're adding a 5 here, so 5 and 2 will give us 7. Now 3 from 7 is 4, and 2 minus 2 here will be 0, so we have 4, 0, and we bring down the 1. We're doing this very much like the standard algorithm for base 10, right? So 4, 0, 1. Now this number is larger, so let's see if we can do better than 3. So we'll try 43 base 5 times 4 base 5, and we notice that 4 times 3 is 12, which is 2 5s and 2 1s. So we put the 2 here, and we put the 2 up there, and 4 times 4 is 16, and 2 is 18. Now how do we write 18 in base 5? That's 3 5s and 3 1s, right? So we can see that 3, 3, 2 is going to work. It's smaller than 401, so we go ahead and multiply 4 into 4, 3. We end up with the 3, 3, 2. We subtract, and if we do it the way we did up here with borrowing, etc., we end up with 1, 4 base 5, which of course is where we stop. So we get 34 base 5 with a remainder of 14 base 5. So notice that this is much shorter, but there's a lot more involved, right? As far as having to multiply in base 5. So it's a matter of choice. Some people like the shortness of this, some people like the simplicity of this. So either way, they're both correct ways of dividing in base 5 or in any other base. You just have to adjust based on the base. All right, how about giving you a break from other bases now? All right, so we have one method which is really nice for doing mental division. And that, of course, in certain situations where it works, can be very effective. So, what we do basically is we're dividing 5,648 by 8, and we notice that 5600 is a nice multiple of 8. If we know that our times tables, of course, we know that 8 times 7 is 56. So, of course, 5600 is going to be divisible by 8. And we know that 48 is also a nice multiple of 8. So, what we do is we break the 5648 as break it up as 5600 plus 48 and then divide. So, we know that this one is divisible by 8 700 times, and 48 is divisible by 8 6 times. Then we just add those two and we get our result. So a very nice process, but remember, it sometimes works and it sometimes doesn't. So this is obviously geared toward the times that it does work. Another trick we have up our sleeves is using compatible numbers. Now, if I'm dividing 105 by 3, I realize I can break this up into 90 plus 15. And once I do that, this becomes really simple because I know 3 goes into 90 30 times and 3 goes into 15 5 times. Just adding those will give me the result, which is 35. When it comes to using compatible numbers, of course, we don't just have to use addition, we can also use subtraction. We realize 232 divided by 8, that 232 can be written as 240 minus 8. Both of these numbers, of course, nice multiples of 8, right? So we can divide in this way. So we know 8 goes into 240 30 times, and it goes into 8 one time. But be careful here, you're going to be subtracting those to get the correct result, which is 29. We can also use compatible numbers for estimation. In this case, you're dividing 3752 by 6, so you want to go to the closest multiple of 6 that you're familiar with and do the division to get an approximate value for that division. Of course, it is not exact. Now that we've handled all 4 basic operations, it's a good time to start talking about the order of operations. And basically, if there are no parentheses present, you just basically go from left to right, perform your multiplications and divisions, and then when you're done with those, your additions and your subtractions. And when it comes to multiplication and division, they have no priority over each other. It's just left to right, whichever comes first. Same with addition and subtraction. The multiplications and divisions are performed in the order they occur, as we said, and the additions and subtractions are performed in the order they occur. Let's look at a couple of examples before we end this lesson. I would like to expand on what was given in our last slide and tell you about the general order of operations so that when we encounter it again, we'll just get extra practice. So one way that we like to remember the order of operations is using the mnemonic PEMDAS, and I'm going to write it like this from top to bottom. Now, P here stands for parentheses, but And we used to go with PEMDAS, but my preference actually in recent times has been to use G rather than P, and I'll let you know why that is in a second. Because sometimes you have more than one set of grouping symbols, such as brackets, and then within them parentheses, and then within them other parentheses. So I think it's better to remember this as GEMDAS rather than PEMDAS, because the G stands for grouping symbol. So you may have braces, and then within them you may have brackets and then parentheses, etc. So the trick with these is to work your way from the inside out. So you take care of the innermost grouping symbol and then move to the next level, and then move to the next level till you've taken care of all the grouping symbols. The E here stands for exponents. In other words, after the order of operations are observed with respect to grouping symbols, you take care of your exponents or exponential expressions, and then you move on to multiplication and division. And remember, with those, neither has seniority over the other. The point is that you go from left to right as you encounter. And then when you're done with those, you go to addition and subtraction, again left to right as you encounter. All right, let me bring a couple of nice problems for us to look at now. Okay, what if we were to do this problem? See, in this case, we have a grouping symbol in here, and we'll take care of the operation within, right? So we have 5 squared divided by 5. I can drop the parentheses now because they've served their purpose, minus 2. Now, moving down the order of operation priority list, we move on to exponents. So we take care of the 5 squared, which is 25, divided by 5 minus 2. And now we're down to these 4 operations. So we're going to go from left to right, handle any multiplication or division now. We have a division, so we take care of that. 25 divided by 5 is 5, minus 2. Finally, there's only one operation, and it's in this group. So we're going to go ahead and subtract, and we get 3, like that. All right, let's take a look at one more problem. Okay, so here I've written another problem. I want you to go ahead and try to see if you can come up with the answer on your own, and then come back so we can compare our answers. All right, so if you notice in this one, we do not have any grouping symbols, but we move on to the next level of priority, which is exponents. So we go ahead and take care of the 5 squared. Notice I leave everything else alone except the one thing that I'm taking care of. All right, so now we're down to these 4 operations. So we're going to go ahead and go from left to right, multiply and divide as we encounter. Notice that some people erroneously think that multiplication comes before division. Not so at all. These are what we call equipotent. That means neither has seniority over the other. You just go left to right and you perform as you encounter. So starting on the left here, we go ahead and take care of the 18 divided by 9. That gives us 2. So we have 2 times 25 divided by 10 minus 5. Again, going from left to right, we notice we encounter a multiplication. So we go ahead and perform it. All right, now we notice that going left to right, we have a division to take care of. 50 divided by 10 is 5, minus 5. Now we're ready to go ahead and perform that. And of course, we end up with 0. So all that work for nothing, right? No, not quite. 0 is an important number, like any other number. All right, so that pretty much wraps up our lesson. Let's go ahead and go on with our tradition of looking at some homework problems now. All right, so here we're given that 42 divided by A is B. We want to find out what 42 divided by B is. All right, so we start with 42 divided by A equals B, right? Now notice that given an equation, we can go ahead and multiply both sides of that equation by the same number, right? So we use that fact to go ahead and multiply both sides of this equation by A. Now that's going to give us 42 equals BA or AB. Now we're trying to find 42 divided by B, right? So all we have to do is go ahead and divide both sides by B, and we end up with these B's canceling out. So we end up with 42 divided by B equals A. All right, so that's one way to handle it. The other way is to notice that just using the definition of what 42 divided by A equals B means, remember 42 divided by A equals B. Let's look at a quick example. What does 6 divided by 3 equals 2 mean? It means 3 times 2 equals 6, right? So using that kind of understanding, what would this mean? This means that this implies that A times B equals 42. And now, since you want to know what 42 divided by B is, you would go ahead and divide both sides by B. And you would end up with 42 divided by B. Once again, these B's cancel out. You would end up with A. So whichever path you take, they're both fine, and you'll get to the same result, okay? That's how you would handle something like that. All right, here we want to use partial quotients to divide 2966 by 22. We did one of these in the examples, but I thought it would be good to see another example of this. So we have 2966 divided by 22. Now, we just go but what comes very easily to us, right? We can see that we can definitely fit 100 of those in here, right? So we start with 100 times 22. That gives us 2200. We go ahead and subtract. We get 667. So 766 is still there. And we can try 40 will be too much, right? So we can do 30. So 30 times 22. Can you do that without a calculator? I hope by now you can. So 30 times 22 we can think of as 20 plus 2, right? Quickly, that's 600. And quickly, that's 60. So 660. We go ahead and subtract. We get 106. All right, now we know that 5 22s, that would be too much because that would be 110. So we can try 4. That gives us 88. And we go ahead and subtract. 8 from 16 is 8, and 8 from 9 is 1. So this is where we would stop, of course, because there are no 22s inside 18, and when this number is less than that number, we stop the process. So we go ahead and combine these on the right side. We get 134 with a remainder of 18. All right, so that's the partial quotients algorithm that we've done a couple of times now. All right, let's take a look at this problem. It says pick a number, so we don't know what it is, so we'll just call it x. We're going to double it, so 2x. And we're going to multiply the result by 3, so like so, right? Then we're going to add 54. And we're going to divide by 6. Finally, we're going to subtract the original number. And we want to know if the result is always going to be the same. Well, let's see if we can simplify this to get close to an answer. So we know that 3 times 2x is 6x. So we have 6x plus 54 divided by 6 minus x. Now, you know that when we have an expression of the form a plus b over c, that's going to become a over c plus b over c. So, and you can see this is kind of like the definition of combining like fractions in reverse, right? So we can write this as 6x over 6 minus or plus 54 over 6 minus x, right? Now 6x over 6, as you know, the 6's cancel out, so you get x plus 54 divided by 6 is 9 minus x. So notice that the x's now cancel out, and we're going to end up with what? With 9. So is the answer always the same? Yes. And what is it? It's 9. So kind of a clever way to get you to practice the order of operations, as well as introducing a little bit of algebra into the mix. Here's a similar one for you to try on your own. And I think that's probably a good place for us to call it the day. So at this point, take care, and we'll see you for the next lecture.